Yeah, okay, so let me just start. I'm just going to share my screen to talk a little bit about the SIG.
Sure. Do I need to disconnect it or?
Yeah, I'm not sure. Let me check if. Okay, yeah. Can you disconnect? Yeah, please. Yeah.
Stop share. Okay.
Yeah. Yeah. Okay. So welcome everyone. So this is like our second colloquium on machine learning and dynamical systems. I just want to give a little bit of a little update about the current tracks. So currently we have 5 tracks. So one on deep learning, and then we had the inaugural lecture by Wen and last month. And then another track will be on reservoir computing. And then today we have Juan-Pablo Ortega, who will be talking about reservoir computing for dynamic processes. And then we have another one on dynamics of games. We'll have a lecture in January by Sebastian von Strien. And then we have 2 other ones on biological and medical sciences and control theory and reinforcement learning. So we'll probably have tutorials and reading groups about on these tracks. And yeah, so now I'm happy to introduce Juan-Pablo Ortega. I will be talking about, okay, let me just give you, yeah, can you just share your screen again?
Yeah, I will. Wait a second.
Yeah, it will be reservoir computing for the learning of dynamic processes. Yeah, thank you. Yeah.
You see it well?
Yes, we see it well. Yeah, thank you again.
Oh, okay. Yeah. Let me see if I can pass the pages. So thanks a lot, Boumediene, and thanks also to Robert for organizing this special interest group. And well, this effort is very much appreciated, not only by me, but by everybody I talk to. And well, it's good to keep the community together in these complicated times. So as Boumediene just said, this is going to be a reservoir computing talk. And I'm going to try in the next hour. It could be that I need slightly more than 1 hour. So it would be 1 hour, 1 hour, 5, 10 minutes. So what I will try to give you is a snapshot of what research, well, personal and by people around me are doing in this field. And I will try to put together, or at least to put in context, what we do with what other people are doing. And since this is, well, an interest group on dynamical systems and machine learning, so I will try to emphasize those 2 points. So in that respect, you see that well, I will divide the talk basically in 2 parts. The one, it will have to do with reservoir computing and how it helps to model and to learn input-output systems. And there we have quite a few results. And so, as I said, it will go very fast. I apologize in advance because in 1 hour I cannot give you all the details, but if at least you get a taste of what we do and what we are interested in, that will be already quite nice. And then there is a second part that will have to do with dynamical systems, where let me put it this way, what we know, or from the point of view of theoretical results, we don't have as much as for the other case. But in any case, I will try to show you what I think is important, what are the leads that we have collectively, and anyway, at the end, if you want, we can have a discussion about what the situation is. And well, a general disclaimer here, so I'm not giving other names as authors in this talk, because what you are going to see here is a melange of many works that has to do with the discussions with many friends and co-authors over the years. You have here a few names, but there could be even more. So so let me tell you in a nutshell what this is going to be about. So in the title, you see that there is this term dynamic processes. So what we are going to be doing, we are going to be learning dynamic processes. So this is a collective for 2 dynamical objects. The first one is going to be input-output systems. The other one is going to be dynamical systems, autonomous dynamical systems in discrete time. Most of this talk is going to be purely deterministic, even though we have stochastic counterparts for many of the things that you will see here. I will just give you references at the end. And I hope that well, for those of you who are interested in that case, and I know that there are many, you find in there something that you are interested in. And in particular case of dynamical systems, the object that we will be learning from is the discrete time observations in low dimensions. So we will assume that we don't have full access to phase space. We will be working with, well, like it is the case in Takens type theory, with low dimensional observations of these dynamical systems in a smaller dimension. So and then now it comes the reservoir computing part. So the way in which we will learn it is going to be a supervised learning procedure, and the object, the paradigm that we will be using in order to carry out this learning task, it will be basically a state space system. And well, the only difference between state space systems and basically run reservoir computing is the fact that in the state equation is going to be randomly generated. Sometimes we will have these sparsity features, and then I will impose on the readout linearity, so that, well, the training is very simple, it's fast, it will demand only a linear regression. And but something that I want to say here is that, unlike what you see in other neural paradigms or recurrent neural networks framework, here we will not have access to this state equation that will be generated, as I said, randomly, and it is not touched, it is not trained. Okay, so these are, if you want, the defining features of reservoir computing. So it's this random aspect, and then this simple readout. Most of the work is done for the supervised framework. And then there is a final part that it has to do with the availability of high performance hardware realizations, because this is something that I will not talk about in here, but historically it has had much importance, because well, apart from all these mathematical characterizations, reservoir computing is also a very nice community. So there is a collection of people coming from various fields, computer scientists, physicists, engineers, and mathematicians, like it is my case, and there is this common goal somehow. Even though we have different backgrounds, we manage to talk to each other. So that's something that I appreciate a lot, and hardware people, they play an important role in the creation of this community that has been so fruitful for a number of years now. So mathematically speaking, let me write down equations for you so that you get used to my notation. So if we talk about the input-output situation, the inputs in my case are going to always be the C's that you see here. The outputs will be the Y's, and then the states will be the X that you see here. So in any case, so where we will randomness is in this equation, right? And well, this H that you have here as a readout that constitutes the observation equation will be most of the time linear. So so let me give you a picture so that you see how it goes in a diagram. So you see, ultimately what we want is to make a map between this input, the Z here and the Y. So in order to do that, all we need is to inject the previous state into this reservoir map, this state map. It appears as a closed ball because I want to emphasize that it doesn't. We do not have access to it. We do not train it. The only thing that we train is this H that you see here. So if you never saw these things, for those of you who never had to do anything with input-output systems, the Z's are going to be, if you want, the covariates in a dynamic regression problem, and then the YT, it will be a dynamic dependent variable, right? So suppose that we want to model here, well, for example, the time evolution of the GDP. It is going to be a macroeconomics modeling problem based on inputs that could be, well, several macroeconomic factors like unemployment, interest rates, or financial variables. Okay, so for those of you who are into time series analysis, you could think of the Y as the value of the time series model, and then the CTs as the innovations of your time series model, right? So this is what we call the calibration problem, even though admittedly the notation is or the terminology is suboptimal. So when you bundle these people together, well, what you get is that out of a time series input, you get a time series output, and this is what the diagram would look like. If you satisfy certain conditions that we will study in a second, what ultimately you obtain out of this state space system is, well, what we could call a Bernoulli shift, right? So the output is going to be a time invariant, causal, functional of the infinite past, general infinite, it could be finite, but in general it's infinite past of the input, right? And that will be always denoted by capital H. These functionals that give you what the value of the output is at a certain time as a function of the past of the input is what we will call the functionals. And of course, in this case, they have been created using this F and this H, and that's why it appears in the symbol. So, of course, admittedly, when you talk about state space equations, this is as classical as you can get. Okay, so there is a huge literature that goes since the 50s, going back to great number of names like the ones that you are seeing here: Kalman, Sussman, Sontag, and there are all these names that have been working on the state space systems, basically for the sake of control theory. And then also in filtering theory, it's something that we teach our students how to use these objects in order to encode unobservable factors, for example. So all I'm trying to say with this slide is that this is an extremely classical field where many questions have been studied. There is a lot of mathematics that goes with this, but something that I want to emphasize, that the questions that we are asking here are sort of like unusual, because first we want to do learning. So it's not that I give you the state space system. Actually, the state space system is what we want to learn, right? And at the same time, we have these strong constraints in the objects that we are using. This F is randomly generated. We want to know how far we can go with these randomly generated people, and what is the kind of input-output or dynamical systems that we can model with them. Something that I can tell you is that in a minute we will be seeing these universality theorems that allow us to provide families of systems of this type that are universal approximants. So actually those theorems, they give you an approximate solution to something extremely classical that I emphasize here in bold, which is the realization problem. You see, we have these input-output systems. A classical problem in systems theory is the realization problem. Is well, if I give you the input-output system, do you have a state space system that realizes it? So our universality theorems will tell us that actually there are very large categories of input-output systems, the so-called fading memory category, where even though you may not have a realization, you can actually uniformly approximate a given fading memory input-output system with systems of the type that I told you before. So you see, there is an interplay in the two directions that I find extremely interesting. So very quickly, I have to tell you about two properties when it comes to these reservoir systems. So the first one is the so-called equistate property, because you saw before, both in the picture and in these things that I told you, that you have to work with these semi-infinite inputs, and then you end up having semi-infinite outputs. There is a causal time invariant relation between the two. And well, actually, the fact that I give you just a state space equation does not mean that if I give you an input, you are going to have for sure an output, or it could be that you have even many, right? So when you have an existence and uniqueness property for this, that is, for each Z input, there is a unique Y output, or if you want only a unique X output at the level of the state equation, we say that we have the equistate property. So this property has been extremely important in the developments associated to reservoir computing, and it has been studied in much detail. In the case that we are studying, the fact that this property is holding is what allows us to associate to a state space system an actual honest-to-God input-output system. In this particular case, we will call it a filter, right? So this input-output system that we can associate to a state equation is what we call the reservoir filter associated to this equation here. Okay, so this is the equistate property, and then there is another property, the fading memory property, is a continuity property that serves two purposes. So the first one is a very important modeling feature that you want to have in many modeling situations, which is the fact that, you know, if you have an input-output system, so the output today you want to have to do mostly with recent inputs, not with outputs that are very distant in the past. So if you go to financial econometrics or into macro modeling, you want that, for example, I don't know, the volatility of your market today is obviously going to be much more related with the prices that you saw in the market in the last week and not what happened in 1929, okay? So the way to model that is by imposing continuity on your filters with respect to the topology associated to these weighted norms in the input and the output spaces. So you choose a weighting sequence, you create a weighting norm, this generates a topology. So continuity with respect to this, these norms is what, well, this goes back to von Neumann, but the actual definition, I think, is in this paper by Boyd and Chua in 1985. That's what they call the fading memory property. The fading memory property, the terminology corresponds to what we see in the sense that this example that I just gave you, you can properly articulate it using the so-called or giving the so-called input forgetting property. So the fading memory filters, they have this input forgetting property that tells you that if suppose that I give you two different semi-infinite inputs into your filter, that will take you to two different points in the state space. Well, but it turns out that if you keep feeding actually the same, if you concatenate these two different semi-infinite inputs to the same future input, so this is what I am trying to emphasize with these two symbols here. So there are these two semi-infinite inputs. I concatenate them with the same input afterwards. So ultimately, if these people keep taking the same input for a while, at some point the output, they are going to become indistinguishable. This is what you encode, or this is what you mean by this input forgetting property that corresponds to this mathematically encoded with this weighted norm object feature. So there is another consideration that goes with this fading memory property is that, well, actually this topology, when it comes to uniformly bounded inputs, is going to coincide with the product topology, and that will give us a compactness property that we need in order to prove universality using the Stone-Weierstrass theorem, but that will come in like 5-10 minutes. So in any case, the two definitions that you saw here, they are extremely important, but it's not the only way to state them. So, the first remark that I wanted to say is that a characterization of these two properties is very difficult, I would say impossible. However, there are very reasonable and easy to check sufficient conditions in order to ensure it. So the first one is by imposing, for example, local contractivity. And that automatically gives you in one shot ESP and FMP. And actually, if I give you a state space system, a state equation like this, in which you can find for me many subsets W that are left invariant by the state equation and where you have contractivity, then, well, you will have the ESP and the FMP. You could have many subsets W of this type. It's related to something that has been recently studied. I encourage you to look at this paper by Jenny Peter Ashwin and Lorenzo Levy and collaborators, and where they talk about the possibilities of having different ESP and FMP regions. That's what it's called, this eco index. Anyway, and then the definition that you have of the FMP here is sort of like a local definition, in the sense that in order to define it, I need to have in advance invoked the ESP. So there is a way around it to make it global. And for that, I encourage you to look at this recent paper by Gandhi Manjunath. It appeared in the Proceedings of the Royal Society. It's a great paper, and it gives a very nice alternative definition view on how to study these global concepts that are certainly complex. The other relation that I wanted to emphasize, that in my opinion has has a bright future ahead is the relation of all these ideas that I'm telling you about, that I'm talking to you about, with non-autonomous dynamical systems. So this also has been explored by Gandhi Manjunath, Peter Tino, and Herbert Jega. Well, there are at least a couple of papers, but I think that this should be further investigated because it's first, in my opinion, something that could be very fruitful and is mathematically and physically very interesting. So anyway, so let me shift gears. And so I gave you the elementary concepts that we need in order to be able to talk. So now let me tell you about universality. So you see, we are dealing with the input-output problem. So what I'm going to do here is to tell you about, well, which of these state space families that we want to use as modeling objects, as approximants for input-output systems, have this universality property. Universality here is density property that, for example, in a static situation, neural networks have, or polynomials, or or kernels to some extent. So this is a generic property that you need to study each time that you talk about machine learning paradigms, right? So there are two tools that we will be using. The first one is extremely classical, is using Stone-Weierstrass, and then I will show you a trick that we baptized the internal approximation principle. So so the first one, Stone-Weierstrass, for those of you who do not remember, and Stone-Weierstrass tells you that if you have a polynomial algebra of functions defined on a compact set, basically you have density. So actually with these polynomial algebras, you can approximate anything that you can uniformly approximate basically anything that you give me. So by polynomial algebra, I mean that I want to be able to multiply and to take linear combination of the objects that I am considering for my family. So in order to give you an example, let me tell you about this result that I mentioned already. So something which is extremely simple to prove is that actually state space systems are universal approximants in the fade-in memory category when you are dealing with uniformly bounded inputs. So what I'm trying to say is that whenever I give you a fade-in memory filter, this is a huge category, right? So I'm not assuming by any means that this the input-output system that has this FMP is coming from a state space system. This is truly a very large category. So what this is telling you, or a corollary of this theorem, is that actually I can construct a state space system. There is a state space system that will approximate uniformly as well as we want this filter, this input-output system. And the reason why that is because, well, actually, if you take the product of two state space systems, you get a state space system. The same thing with the linear combinations. You have the details in equations 2 and 3. But then I told you that the Stone-Weierstrass needs compactness. So compactness comes from FMP. Compactness comes from the fact that we are considering the topology of uniformly bounded inputs, this weighted topology. So weighted topologies, you can prove that for any weighting sequence that you use coincide with the product topology, and by Tikhonov, product of compact is compact, even though you are in an infinite dimensional situation. So this is a strong compact topology. So we are not talking about weak or weak start topologies. There is no allowed loop here. So this is honest to God compact, and it's because of this uniform bounded hypothesis that we are. So, but actually, universality in the setup is not that complicated. So actually, you don't need all the families of state space system. Actually, just linear systems are already universal, right? In that case, you need to use polynomial readouts. And if you push me, you can even get it cheaper. So actually, you just need to have diagonal or nilpotent matrices in order to achieve universality with polynomial inputs. And so that's something that has, in the nilpotent case, this has a very nice consequence, and is the fact that well, nilpotent systems, they are going to have finite memory. So well, this tells us that actually is not only state space systems that are universal, it's actually finite memory systems that are actually universal in the fading memory category. So any fading memory input-output system can be approximated by a finite memory one. However, I told you that in the reservoir computing setup, we are interested in linear readouts. And here I'm telling you that you need polynomial readouts. Polynomial readouts is bad because, well, polynomial regressions, they are not good. Usually they are poorly conditioned. We don't want that. What do we do in order to achieve this feature with just linear readouts? In order to do that, we came up with a non-homogeneous version of these state-affine systems that were introduced already many years ago by people like Michel Flies and Normand Sirot in France. And in the context of state space systems with forward-looking flows. So what we did is, in order to adapt that to our semi-infinite situation, we had to come up with a non-homogeneous version of it. So who are these people? These people are something very close to linear systems. However, here, instead of having a matrix, instead of having an A, we have basically a polynomial on the inputs with matrix coefficients. So these people, they are well behaved and they form a polynomial algebra with linear readouts. This is what is extremely important for us. These people, they are universal in the category of state space systems, in the fading memory category, but we achieve this universality with linear readouts. We don't need to go polynomial in the readouts. So here is the statement. And let me point out something. You see, for those of you who are used to the continuous time setup, the continuous time setup is always much nicer than discrete time, because you have these functional analytical tools, you have differential equations, is nicer. This, and for example, this universality, if you want to achieve it with this type of readouts, well, it suffices to use, and that's something well known from the times of this 1985 paper by Boyd and Chua. Well, you just need bilinear systems, all right, if you are in the continuous time setup. So so here you see that things in discrete time, they get much uglier. So you need more algebraic complexity. Anyway, so but here something that we have missing is that, as I will tell you in a few minutes when we talk about applications, there is a very important paradigm in reservoir computing, which is the equistate networks. So the equistate networks, these are recurrent neural networks, which are the, let me put it this way, they are the closest relative neural networks that you can have in the recurrent setup, right? So those we cannot prove their universality using Stone-Weierstrass. For that, we need something else. And the way we prove that is by using this internal approximation theorem or property that tells you that basically is very simple and very intuitively, intuitive to comprehend. If I give you a couple of functions, right, state space, if I give you a couple of state space maps, if they're L infinity close, then if these people happen to have this ESP feature, they generate a filter. Actually, then the associated filters, they are also going to be close. So this is a very simple continuity feature. It's a non-trivial one because these Fs, they live on finite dimensional spaces, while these filters, they live on infinite dimensional spaces, right? So you need to sit down and do it. But actually, it's by using this property that by using the universality of neural networks, we are able to prove the universality of equistate networks. So as I said before, the equistate networks are the system that you see here. So it's a system. Is a state space system in which you have a neural network-like state equation, and then you have a linear readout. Okay, so these people, they are also universal in the sense that I told you before. So this is as far as universality it goes. However, there is an important leg missing in these results that I gave you. The first one is that I told you that you see, when we are doing reservoir computing, we want to have randomly generated people. right? And that's something that I didn't look at in these results that I told you about. I told you that there is an ESN or there is a SAS that is working as a universal approximant, but I didn't tell you anything about randomness. I didn't tell you that that can be achieved. Let me go back to the previous slide, using a randomly generated A, which at the same time is sparse. And that's something that we know works from applications. So how do you prove that? So there are two ways to answer that question. The first one is by using standard stochastic analysis techniques, right? And that's something that we did in these two papers that you see here. This G is Gonon, Grigorieva, Ortega. So these are two papers. One of them, it was accepted last week in JMLR, and the other one is under revision for the Annals of Applied Probability. So, by the way, it could be that the referees of these papers are in the audience. I wanted to thank you because, well, these are very technical and very thick papers. So I feel pity for the referees of this paper. In any case, if you are there, thank you very much, because well, these people, they did a great job, and I'm sure that it took quite a while to do it. So in any case, this would be the stochastic analysis approach to the problem. But then the one that I chose to show you quickly in the next 10-15 minutes is the use of random projections, that is the so-called Johnson-Lindenstrauss lemma, in order to explain this phenomenon. It's something that I like very much. It's not that complicated to understand, and then I will give it a try in the next 10 minutes or so. So in order to do that, I need to give you a first result, which is, if you want, the semi-infinite input transliteration of an old result by Sandberg dealing with forward-looking systems, which is basically that, well, if you have a fading memory system, which happens to be analytic, then, well, you have a Volterra series expansion. Volterra, for those who never saw this before, so Volterra is basically a Taylor series expansion of an object that lives on this infinite dimensional space of inputs, of semi-infinite inputs. So if you do Taylor, this is what you end up obtaining. So, and actually, the important thing about this expansion is that when you truncate it, you have a very nice uniform control on the error that you commit. And here, there are two types of truncations that you can have. You can truncate on how many steps you go back into the past. That would be the L truncation, right? And then another truncation possible is what is the highest order of the monomials that you have in here with the C's, how many of those you are willing to take. So, so if you truncate on the degree of polynomials, is an honest to God Taylor bound. So this is what you see here down in the right. And then the other bound, which has to do with how far you go into the past, has to do with a fading memory type of bound that has to do with a weighting sequence that corresponds to how you characterize the fading memory property of this filter that you are expanding in a Volterra series. Okay, so this is important because it will allow us to prove a different type of universality, a stronger type of universality. So let me tell you in a second what I mean by that. So so in order to do that, what I'm going to do is I'm going to show to you that actually this truncated Volterra series expansion admits a state space realization. And then in order to do that, you need these ingredients that you see in this slide. First, the state space is not going to be an Rn, it's going to be a tensor space, right? So it's the vector space of tensors of order L, right? L is going to be the truncation in the past, and D will be the truncation having to do with the order of the polynomial we are using. We have these van der Monde vectors, so we need an order lowering map. It doesn't matter what the technicalities are. All I want to show you is that you can formulate a state space equation on this tensor space, right? Which, if you choose the lambda according to this prescription that you see here, which is extremely explicit, then the ESP and the FMP are going to hold. It will have, therefore, a unique solution. And then the filter associated to these unique solutions is such that well, the output that you will obtain actually is going to be a collection of monomials, which basically actually span all the monomials that you need for the Volterra series expansion. So the reason why such a construction is important is because you can prove that then by reading linearly the output of this state space system that generates for you all these higher order monomials in this tensor space, then well, actually you can approximate any filter that has this analyticity and fading memory property that we had in this Volterra series expansion, the theorem. Such an object actually can be expanded, but this truncation actually coincides with the readout of a state space system, which is what we call this signature state affine system. So the reason why we call it signature state affine system is because it has a certain similarity with what is called in rough path theory, and if you want, in the theory of control ordinary differential equations, the signature process. I'm not going to get into that because I just don't have the time to explain it, but there are certain similarities with that one. And among those, the fact that it exhibits these strong universality properties that I will tell you about in a second. So what do I mean by a strong universality? You see, when we were dealing with the universality of equistate networks, or SAS, well, I was telling you, you give me an FMP filter, and then I will construct for you an ESN that fits or that approximates this given U, okay? However, for you change on me the U, and then you will have to change the ESN that I used to approximate it. However, in a situation like this, if you change for me this U, well, the approximant state filter will be the same for everybody. The only thing that I will need to change in order to adapt this approximation to a different U is this linear readout. So that's why we call this a strong universality, because the approximant state object is always the same for everybody. And in order to adapt to a new U that needs to be approximated, all you need to do is to change this linear readout. In plain English, all you will need to do when you do this interact with an input, a given input and output, it will be to rerun a linear regression in order to reparameterize, retrain the system to adapt it to a new U. Okay, so that's what we call a strong universality. The proof of what you just saw is very simple, because it just comes to matching the coefficients of the Volterra series representation of U, right? And then, yeah, well, there is some numerical efficiency that we could discuss here that has to do with the fact that, well, we have formulated this, in principle, infinite truncation, something recursive in a state space form. This line is mainly talking to those who have done signatures in continuous time, where you have to apply, when you have to compute all these iterated integrals that are very convoluted. In this case, when we are using discrete time modeling and well, we are taking this approach, it goes much faster. So in any case, we have this strongly universal object, but I still didn't tell you how to go about randomness as a sparsity. And that's the reason why we got into this SIG-SAS system, this signature state affine system. I told you about the signature part. The reason why we call it SIG-SAS is because, well, if you sit down and we would have 10 more minutes, I would show to you that this is actually also a state affine system of the type that you saw before. So anyway, in order to achieve sparsity and randomness, the idea is to take this SIG-SAS system, which in principle would be defined in a very large tensor space. The dimensions here, they could be huge. So the idea is to use a random projection. So there is this Johnson-Lindenstrauss projection lemma. For those of you who never heard of it, is a beautiful result that tells you that, well, whenever you have a Hilbert space, so this is an L2 feature, because you use the parallelogram rule all the time, you have a potentially very large dimensional Hilbert space. So you give me a bunch of points in this Hilbert space. So what this theorem tells you is that, well, actually random projections, and by random projections, I mean that you take a matrix whose entries are randomly drawn out of basically the normal distribution with a variance that is given by the lemma, right? And then well, actually the distance between these points that you have in this high dimensional Hilbert space, when they get projected by this random matrix to something smaller, actually there is a relay between the dimension of this projection space and basically the degree or the disturbation, the distortion in the distances between these points q that you will have in this project space. So that's a purely geometric, if you want, fact. But actually, that fact can be also used in order to project not only points but also state space representations, and that's what we do in this theorem that you see here. So I take one of these random projections, and then actually I can take a state space system that lives in this lower dimensional projected space, and then I can bound the error that I'm going to commit in this projected space. If you look at the statement of the Johnson-Lindenstrauss lemma, which I'm not going to show to you because we will not have the time to analyze it, well, the cut in dimensions is logarithmic. Okay, so it's a significant dimension cut. Obviously, the higher the drop in dimensions, the worse is going to be the approximation, right? So there is this balance between dimension cut, dimension reduction, and then the degree of the approximation, the epsilon up to which these two people, this geometry will be preserved. Okay. In any case, this is tell you that you can use Johnson-Lindenstrauss lemma in order to project state equations. So the punchline here is, what happens if we take this complicated state space system in a potentially very high dimensional vector space and we randomly project it? So the punchline is that what you obtain is actually a SAS system, but a random one. So what the theorem that you have in front of you tells you is that if you take that huge dimensional state space 6 system and then you randomly project it, you obtain a SAS system in which the coefficients are these matrices, which are random matrices whose entries are basically drawn out of this normal distribution, whose variance is if you want, specifically spelled out. So the reason why this result is important, we believe, is because it gives an interpretation of geometric nature to the reservoir computing phenomenon. Because you see, you generate randomly a SAS, or you generate randomly an ESN, it works. And then what this theorem is telling you is why it works. This works why? Because actually you can see any randomly generated SAS system as the random projection of another system in much higher dimension that actually corresponds to a higher order expansion, Volterra series expansion of the filter that you are trying to model. Okay, so and actually, you see, if you have something here, a SAS in dimension capital N, actually, morally speaking, what you are using is a Taylor series expansion of the object that you are trying to model in dimension e to the power n, right? So that's why it works. So because there is this favorable relation between the dimensions of one and the other. So this was just to tell you about randomness. There is a version of Johnson-Lindenstrauss that allows you to construct these matrices sparse. So if you want, if we do things like this in one shot, you can talk about randomness and sparsity. So anyway, I know that this was very fast and there are all these symbols, but I hope that at least this idea that I just said is a bit clear, because that's the most important idea, I would say, in this part of the talk, is that you see these randomly generated systems, actually they perform well because, if you want, they are the randomly projected version of something in much higher dimension that is specifically devised to approximate well whatever FMP filter you give me, okay? So that would be the main idea that I'm trying to convey to you in this part of the talk. So now let me shift gears again, and now I stop with input-output systems and I go now to dynamical systems. So as I said here, I personally, and I think that us collectively, we have to be a bit modest because we know less, and also because admittedly the problem is much more complicated, I would say. So when I talk about dynamical systems, we will be dealing with in the next 15-20 minutes with discrete time dynamical systems defined on basically compact manifolds. Here I did it in certain generality, so I just give you a map from one topological space to the other. This defines a flow. Anyway, we have a discrete time dynamical system. The trajectories of the dynamical system that this flow generates is basically the iterative application of this phi, which ultimately is going to be either a homeomorphism or a diffeomorphism. And but in any case, this is the data that we will be working with. Or if you want, what we will be working is not with that. As I told you before, we will be working with low dimensional observations of it. So what we will have, as I said, we will encode this as a supervised machine learning task. And then what we will have at hand is, as data, is actually this, in this particular case, scalar observations of this dynamical system. So the goal is, the learning goal here is, I give you these observations of this basically the dynamical system defined on this manifold M, and then just by looking at these trajectories, I am supposed either to reconstruct it or to capture the dynamics of these observations. And this is the only object that we can play with. And here, again, as in the previous case with the state space representations and control theory and so on, of course, the theory here is huge. And I know that there are many dynamical systems experts in the audience. So at least the learnability question, there is something that we can say, because there is theory in dynamical systems that hints to us that learnability is possible. So my favorite argument is Takens, right? The Takens embedding theorem actually proves that learnability is possible. Because you see, for those who are not into dynamical systems or who have never seen Takens before, actually remember the first time that they read Takens theorem, you have to be aware there is some surprising facts that go with it. And it is the fact that if you tell somebody that you need to reconstruct a dynamical system out of a scalar observations of it, it looks like impossible. So just think, for example, of I don't know, a gravitational system. Look at the planetary system, right? So suppose that I tell you that just by observing an apple falling from the tree, you need to reconstruct the entire planetary system. That looks like a crazy statement. And well, in the case of the planetary system, Takens doesn't give it to you because there is no compactness, because this is defined in basically in the cotangent bundle of a manifold which is not compact, right? But in any case, even in the compact situation where this is possible according to Takens, I always found it very surprising and very interesting. And for those of you who never saw Takens before, so what Takens tells you is that, well, actually there is this map, is the so-called Takens delay map, which consists basically on a map that takes the points in phase space to basically a delay embedding in dimension 2q plus 1. Q is the dimension of the manifold where your dynamical system is living. And actually this map is a C1 embedding. C1 embedding means that you have an injection. Its derivative is injective. It exists and it is injective. And since you are defined on a compact manifold in injections on a compact manifold, they are always embedding. So actually the topology that you are going to have in the target coincides with the relative topology. So the reason why that is important is because if instead of looking at your dynamical system on the compact manifold M, you look at it in its representation via this injective map in this R2Q plus 1, then, the dynamics in there, if you just follow which is what I did in this equation, the dynamics using the Takens embedding. So you pull it back to the original manifold, then so with the embedding, then you flow it and then you push it again to this Euclidean representation. Then you obtain dynamics whose flow depends basically on a function that, if you are into learning, that you need to learn out of the data, out of the realizations of this dynamical system. So what I'm trying to say here is that if you just follow Takens and you want to learn the dynamics of the system in this R2Q plus 1 representation, in this Takens representation, all you would have to learn is a function defined on Euclidean space. And that, if this F is not very complicated, if at least it is measurable, we can do that with neural networks, with polynomials if they happen to be continuous, or other universal approximant that you may think of. So this tells us at least that things are not hopeless. And that's actually what has been used for decades now, using embeddology. It has even a name, this field, in order to forecast, to continue dynamical systems, to path continue dynamical systems. There are all these techniques in time series analysis that are based on this idea. So this is by no means new and is very well studied. But in any case, one of the, if you want what put in the map, this reservoir computing is the fact, and you will see it in the original abstract, that there was this paper by Herbert Jäger, you will see it in a second, in which using equostate networks of the type that you saw before, he was able to improve techniques based on Takens embedding. There is this nearest neighbors technique based on Takens embeddology. You forecast dynamical systems with that. So using ESNs, it was possible to improve on that. Okay. So how did you do that? So here I tell you how people come up with forecasting of autonomous dynamical systems using reservoir computing. And here I'm borrowing a terminology by a recent paper by Pietro Verzelli and his collaborators. So he has this nice terminology, and he also points out this relation with the generalized synchronizations that I will evoke also in a minute. And then he says that if you want to proxy a dynamical system, or at least the dynamics of the observations of a dynamical system, you have to proceed in these three phases, which is what people have been doing for years. The first one is this listening. So what you do is you just take the observations of your dynamical system and you pass them through the state equation. This could be a SAS, an equostate network, whatever paradigm you're interested in. And then you collect a bunch of states, right? In a second step that we will call training, you just minimize a loss so that with a given readout, you actually give me out of the state at a given time, you give me what the value of the observation of the dynamical system one time step into the future is, okay? So that's the training phase. Here I'm optimizing with respect to the square, to the mean square error, right? Or the square error, the solution is going to be a conditional expectation. This is an OLS problem, okay? If this H happens to be linear, right? Like in the case of the ESNs. Once you have that, what you do is you close the loop, right? So instead of, this is not an input-output system anymore. What you do is you run the state space equation autonomously by injecting what comes out of the observation equation into the state equation, okay? And then the idea is that if things work well, and if this paradigm really works, the resulting autonomous system actually should be a proxy for the dynamics of the observation of this dynamical system that we are interested in modeling, okay? So this is how people use equal-state networks or reservoir computing for the modeling, the path continuation, the learning of dynamical systems. So I give you two examples. The first one, for historical reasons, is Mackie glass. This is what Herbert Jäger and Harald Haas, they put in this 2004 paper. And here you see this 1,400 factor of improvement with respect to previous techniques, right? That's what made this technique very visible. So here you have a little simulation of how that thing looks like. I here just reproduce the prescription in Jäger's paper. And so here, what you see is basically the proxy and the I don't know, a Runge-Kutta high quality simulation of the Mackie glass TDD. And so I think that up to 3 Lyapunov times, they are basically indistinguishable. Another example that has become extremely popular and very well known in the recent years is the work around Ed Art and his students, well, now former students, having to do with this nonlinear high order Kuramoto-Sivashinsky model for flame propagation. And here is truly spectacular. So let me give you just a picture from their paper, in which you have I think that A is the actual, high quality, I don't know, finite elements solution coming out of directly of the PDE. And this is what comes out of an ESN in dimension, I think, 30,000. And in order to get this, in order to get B, you just need to run a linear regression. So it's truly spectacular. Here, I think that they go to 7, 8 Lyapunov times. It's very impressive in their paper. If you look at it, they have very nice results having to do with Lyapunov spectra and things of that type. So this is to show you that it works. But then before, when it came to input output systems, I could tell you reasons why it works, because we have these universality theorems, we have bounds, we have estimation and approximation bounds that guarantees that the learning is the way it should be. But in this case, this is not the same anymore. So when it comes to theoretical results, the best, in my opinion, that we have so far is this paper by Alan Hart and his supervisors in Bath. So what they proved is that actually they did it admittedly only for the time being for ESNs, but I think that more general versions are coming. And what they proved is that there is a pseudo randomly generated, the pseudo, I would have to explain it to you, we don't have time for that, but there is a pseudo randomly generated ESN such that you can train this W so that, the resulting autonomous dynamical system, autonomous using the recipe with the listening, training, forecasting routine that I showed to you before, well, this autonomous dynamical system is going to have a normally hyperbolic attracting submanifold in which there is going to be basically topological conjugacy with respect to a tokens like dynamical system that you give me. Okay, so the hypotheses that you need to satisfy are very close to what Takens needs for his embedding theorem. So the reason why that is also related with another extremely classical concept, which is that of a generalized synchronization. So the way in which basically this topological conjugacy happens is via what they call the equistate map, which is actually in the language of dynamical systems is what is well known as a generalized synchronization. So for those of you who never saw generalized what a generalized synchronization is, there what you have is basically a dynamical system like the type that we saw before. You have its observations, and then now I give you a state space system, and then you drive it. So the inputs are going to be the observations of this dynamical system. So you see that you say that you have a generalized synchronization between the dynamical system and this state space system driven by the observations whenever you have a map that synchronizes the evolution of the dynamical system in phase space with the states of this state space system. Okay, so in the engineering language, what this would amount to is to have basically a slave master configuration between the dynamical system, which would be the master, and the state that becomes the slave. But this is not anymore the observations. This is the evolution in phase space in full glory. Okay, so anyway, this is something, as I said before, extremely classical. The literature started in the 80s, 90s. It was made basically by physicists, but when it comes to learnability, and that's something that recently people have realized in the context of reservoir computing. So I encourage you to look at these two papers. The first one by Lou and Bassett, and the other one by Pietro Vercelli and his collaborators that I cited before. So whenever you have such a synchronization, it turns out that if I give you this state space system, then if this synchronization happens to be injective, then you are able to come up with a readout that will actually give you, just by construction, the dynamics of the observations of this dynamical system that you want to learn, right? So in other words, if you want to learn the dynamics of the observations of a dynamical system using a state system, you need, or one way to do it is by coming up with an injective and sufficiently well-behaved generalized synchronization. So, and actually something that is, in order to put this in context with other things that we saw before, actually Taken's theorem, it can be formulated like that. So you see, if I give you this state space system, in which a linear one, in which the linear disconnectivity matrix is just basically a lower shift matrix, so it's a bunch of zeros with ones under the diagonal. And then you have this input mask, which is this just 1 zeros vector. And well, it turns out that if you use Taken's theorem in this context, what you obtain is a continuously differentiable embedding that at the same time gives us a synchronization between the dynamical system to which we applied Taken's embedding and this state space equation. Okay, so in that case, learning the system would have to do with learning this map, right? Which in this particular case is very well behaved, because we know by Taken's theorem that this map is an embedding, and therefore we have guaranteed at least that we have continuity, right? So the important idea that goes with the use of reservoir computing and state space systems is that, you see, if you do Taken's, right, well, the state equation that you have, the analog of our reservoir system, would be extremely simple. It's just linear. However, this map is very complex. So what ultimately we are trying when we do reservoir computing is to make the state equation more complicated. It could be a SAS, it could be an ESN. And that's how we manage to make this H functionally simpler and therefore easier to learn, easier to train, because we want it to be linear. And that's the only way, right? Either if we want to make it simpler, then the non-linearities in the problem, they need to be cornered somewhere else. So that's ultimately what we are trying to do in reservoir computing, or if you want, that's an interpretation of what we want to do in reservoir computing when we are trying to solve these type problems. So let me end the presentation by telling you that you see something very important is regularity, because you see, if you need to learn, let me go back here, this map, right, or actually here, if you need to learn this map and this F is very complicated, then the training is going to be either very expensive or basically impossible. So we want to make sure that this F is actually well behaved. And that's something that was very well studied in the very beginning when these generalized synchronizations were formulated. There are all these papers that talk about the fractal nature of them, and that's when they talk about weak synchronizations. There are beautiful physics papers that have to do with this phenomena. Very also easy to read reviews by some people, so you will see that they are cited at the end. And but in any case, in order to have learnability, we need this injectivity, and then we need that they are not wild, right? We would like to have them at least continuous, and if possible, C1, right, differentiable. So so that's something that we recently proved. So we have these theorems that you will see in a second. So the first one is just a little lemma that tells you that, well, whenever you have the equistate property, actually synchronizations always exist. And actually you can get them out of basically the filter whose existence is guaranteed by the ESP. So if you, well, yeah, so that's a fact. And then actually, and that's a technical point, these synchronizations, they satisfy this iterative relation that is very important, because actually all these synchronizations, they are going to come out of the fixed point in a Banach type contraction problem. Okay, so if you just follow this lead that I just mentioned in words, well, actually you can prove that whenever you have local contractivity and you have continuity both in the dynamical system and in the state space equation that in the state equation that you are using, then you will always have continuous synchronizations. So and for that you only need local contractivity. So it could be that you have various local compact regions where you have contractivity. That means that you could have many generalized synchronizations. That talks much to the work of Peter Ashwin that I mentioned before. So in any case, this is when it comes to continuity. When it comes to differentiability, the situation is identical, except for the fact that you need to satisfy a relation between the derivatives of the state equation that you are using and the tangent map of the, if you want, the L infinity norm of the tangent map that of the dynamical system that you are trying to learn. So and this norm, let me emphasize, is finite, because we are always working with compactness. So whenever there is not compactness, we don't know how to do it. And another thing that I have to warn you against here is that if you want these solves in this specific case, the differentiability and continuity question, but we didn't solve yet what is in the context of Takens theorem, if you want, the most difficult question, which is injectivity and immersivity, right? So that remains an open question that we are working on. So I finished with this. So there are other topics that you may be interested in, because as I said, since this is dynamical systems and well, I chose to go fully deterministic, there is a stochastic counterpart to many of the results that you saw in here. For those of you who are into bounds, I already said before that we have approximation bounds and risk bounds for these approaches, or at least for some of them, at least ESNs and SAS, we figured them out a couple of years ago. And as I said, they're about to appear. And also, well, about the dimensional reduction. And well, for the reservoir computing people in the audience, you know that there is a huge literature in this memory and forecasting capacities problem. So we also have some contributions to it, and that were published thanks to Boumedien's volume. There is a very nice volume that Boumedien put together, and it contains very nice articles. I'm not talking about ours, but in this interplay between machine learning and dynamical systems, there are fascinating things there. So anyway, and then let me conclude just by flashing the references so that they are recorded for those of you who will not download the slides, so that at least you have them in the recording. So thank you very much. I will stop here, and thanks for your attention.
Thanks a lot. Thank you very much. Any questions?
Yes.
Yeah, go ahead.
I was wondering how you make a complicated xt, and then you take age of xt, and it becomes simpler. That's a little bit counterintuitive.
I guess that you are thinking of this slide, right?
Yes, like about 5-10 minutes ago.
Is this a remark that I made in here, right?
Exactly.
You see,
it didn't look intuitive to me.
So you see, by the time that, so here you have this equation and the observation equation, right? And here I gave it to you in the case of Takens. So we know this is true for sure, because Takens tells us that you know, just by choosing the age as I wrote in here, actually I am recovering the dynamics of the observations of the dynamical system. In this case, since we are using Takens, we are using this very simple linear system, but the price to pay, because the dynamical system per se could be extremely complicated. So that complication shows up in the age, right? So, however, we know that we can do this with other paradigms. So for example, with ESNs or SAS, in which the ESN is not linear or simple anymore, is something neural network-like. The SAS, you saw them before, they are also complicated because they have this polynomial dependence on the input. But we know that in practice, by taking H as linear, it does work, right? So the reason why that is, for ESN, I can give you a reason, which is this Hart et al. Result that I quoted before. So let me show it to you. Right? So we know that it works because these people proved it. There's a topological conjugacy between the attractors of the resulting ESN and the dynamical system that we want to proxy. Here, the H that we had before, here is just a matrix, right? So here, it is like that. I mean, these people proved it, and if you want, the goal here is to show that the phenomenon that they were able to establish here theoretically as truth is actually more general than that. And why, you know, making the relation between Takens and that, this comes out as a natural lead, right? So that's all I meant to say. So for ESNs, it is actually something that is true, or at least partially true, according to the statement that I read to you. But it is my belief, and that of other people that I talk to, is a much more general fact, is a much more general phenomenon.
So is this a beautiful, elegant exploitation of the attractors in the dynamical systems?
Well, that's a good point. So, this only works for stationary regimes, right? So this kind of learnability, and it always works when you are working in a stationary regime. Well, translated in the language of dynamical systems, that means that you need to be in the attractor, right? So So at least in a lobe of it, because you see, when it comes to applications, we could also talk. Whenever you have multi-lobe attractors, things get complicated. So, which is not the case for this TDD that I showed to you. But if you try to do this with Lorentz, for example, capturing the two lobes sometimes is complicated. But that's a different story. But the answer to your question is yes. So this works when you are evolving in the attractor.
Thank you so much.
Thank you.
Any other questions? I see a question from Pietro Verzelli. Yeah, you can ask it directly. Yeah.
Okay. Yes, my question was about the invertibility, because I think that the invertibility of the phi, the flux, is required, right? And whether you know something about when this assumption doesn't hold anymore, if there are some way to circumvent it.
No, Pietro, no. Here is the invertibility is badly needed. In all these results that I showed to you, starting with tokens, right? Phi needs to be a D-field. So you need invertibility, right and left. Already in the formulation of the delay map, you see that there are all these phi inverses everywhere. So so the two main limitations here are the invertibility and then the compactness. So in these results that we proved, I had never worked in that before in my career, but there I could see how important compactness is in this field, right? So from the point of view of the applications that I am interested in is a huge handicap, because if you want to do applications on mechanics or in robotics, compactness is truly out of the window. Everything leaves. I mentioned examples having to do with celestial mechanics, and everything leaves on cotangent bundles, right? So even if you are in the cotangent bundle of a compact manifold, this is not compact. So then in principle, this Takens theorem, it doesn't hold anymore, as it is the case with the results that I stated.
Okay, thank you.
Any other questions?
Maybe I can ask one.
Yeah, please go ahead. Yeah.
So I'm curious about with this fading memory property and the discrete time formulation. Does that mean essentially that if you have some system for which an existing kind of reservoir setup works, that if you have much higher sampling rate, really high fidelity data, that at some point that setup will stop working because you really have very many time indices for which the memory is relevant?
You see, well, all these observations that I made about fading memory, input-output systems, actually forgetting, there, at least in the formulation, at least in the statement that I used, there the only hypothesis that I used in there was uniform boundedness in the inputs. And there you have a certain independence on the weighting sequence. So that is, if you have uniformly bounded inputs, actually the rate at which you forget you see, if you are fading memory for one weighting sequence, you are for all of them, right? So you don't see anymore the rate at which you forget. This is for discrete time. For continuous time, on top of uniform boundedness, you need to assume equicontinuity. So I don't know, because I honestly have to tell you that I didn't think seriously about it, how it talks to the sampling frequency type of question that you just asked me. But well, I think that that's the direction in which one should look at, because yeah, in order to answer your question, the way I would tackle it is by going continuous time, formulating the condition continuous time, and then to look at how it behaves with respect to different discretization rates. And but then the answer to what you asked me, I don't know. So I know how I would go about it, but I don't know what the answer is.
All right, any other questions?
Maybe I can ask one more if you don't mind.
Yeah, please, yeah.
Sure.
So I'm also curious about the role of sparsity. We talked a lot about randomness, but how important is choosing a sparse A, for example, especially when you have partial observations? How important is that?
Well, the obvious answer is computational considerations, right? So you see some of the reservoirs that people use in order to accomplish these nice applications that they talked about, they are pretty big. So in the case of Jaeger's paper for Mackie glass, I think it's a reservoir of dimension 1,000 or something like that. And then Ott and his people, I think is several thousands, right? And you see, I've seen many papers dealing with applications to forecasting and so on. So you always work with reservoirs that is A's of several thousands when it comes to order of magnitude. So of course, if you can treat this A as a sparse matrix, then this thing runs much faster, right? So that's the obvious consideration. Then it comes to you see that the reason why I was telling you about this Johnson-Lindenstrauss is because somehow using stochastic analysis, we are able to prove or to state pack bounds that show that with randomly generated people, we are able to basically uniformly approximate anything you give me, right, in the faded memory category. But we didn't say any way to do that with sparsely chosen people. So the only way we were able to do that is by using this Johnson-Lindenstrauss, this sparse version of Johnson-Lindenstrauss. And so all I'm saying is that we can explain why the sparsity that people were using from the very beginning in applications, because already in this 2004 paper that I showed to you by Herbert Jäger, there he uses already, I think these are matrices that are full. I mean, the sparsity is 99%. So these are basically empty matrices. Nevertheless, he gets these fantastic results. So all I was trying to show to you is an argument why using the sparsity, you could still, you could prove theoretically that does the job, right? But I don't know if that's exactly what you are asking. Does that answer your question, or?
I mean, in part, I understand that it's computationally, makes things easier. But I've seen some recent work that suggests that, like I'm thinking of Pantelis Vlachis in 2020 was comparing to Arnold, and one of the key kind of conclusions was that for partially observed systems or systems with memory, that the reservoir computers kind of struggled. They predicted well in short term, but struggled to really capture memory, and that was the improvement that you get from RNNs. And so I was wondering if you could comment on that. And I have some personal thoughts on why that relates to sparsity, but I'm curious if you can comment also on the amount of memory that reservoir computers can hold.
Yeah, I share that because I know the paper that you are talking about, and I heard Pantelis's talk in the Fields symposium that Boumediene organized, and yeah, well, all I can say is that yeah, it's a fact. It's there, and I agree with his conclusions. But in all these bounds that you are able to find in our papers and so on, there is nothing that could explain it. So yeah, it's great empirical work, but unfortunately, I think it could be that I am missing somebody's result here. And but yeah, theoretically, I personally do not know how to explain it. So yeah, but that's a very good observation. Yeah, indeed.
Thanks for your talk again.
Yeah, Ludmila, did you want to add something, or I think it's yeah, okay. I mean, Ludmila wrote something on the chat. I don't know if you want.
I see it.
Yeah. Okay. Yeah. All right. Any other questions or comments, or?
Maybe just the name of the paper that was just mentioned, because I couldn't hear it properly. Maybe write it in the chat or something. The paper about the sparsity.
Sorry, I just unmuted myself now. I couldn't find the button. So it just related to what I wrote in the chat. So and concerning the question that was before that. So I could see other also papers of the type of Blasch's papers, where they come to a completely opposite conclusion to what they claim in their paper. So I still don't know how all these body of work is related to each other. Whether the results that they get for the reservoir computers is because of a better training of RNNs, or because of more effort was put in RNNs, or because some unlucky configuration of reservoir computer type ESN was chosen. It's very difficult to answer to that question. And I saw a couple of papers, and I can also put that at some point to a chat if I find it right now, where they actually claim the opposite, that reservoir computer systems, ESNs, they learn better the partial observations of dynamical systems than, for example, RNNs. So it's very difficult to say which one gets to a more fair conclusion and due to what modification in the empirics. So this was just my comment. So I still don't know what to make out of those papers. Which one reports a more precise analysis? Thank you.
Thank you. So Manjuna, did you want to ask your question directly, or?
Yeah, good afternoon, Professor. Thank you for your wonderful talk. I'm just wondering, in a hardware implementation of our ecostate network, what is hard to implement, memory or the nonlinear nodes? So by memory, I mean storing data. It's like not the memory in the network, but just something like you have a buffer and you hold data, which is hard to implement. Thank you.
Look, about memory, I don't know, because, well, about memory, I don't know, because you see all the hardware implementations that they have seen and that they have worked with, because you see the reason why I got into this business actually had to do with hardware implementations when I was still in France. And then there were these people using time delay differential equations to implement reservoir computing paradigms. So, but there is no memory buffer, nothing. I mean, there it was just a nonlinear system whose time discretization had to have nice eco and fading memory properties. So what I know, when it comes to hardware implementations, is that what is difficult and expensive to implement is nonlinearities. So I have this project with these IBM people here in Rüschlikon next to Zurich, and they have a neurocomputing unit in which they are basically developing all these systems that use, if you want, something close to what we could call a reservoir effect, in order to come up with computation in the sense that we were discussing in this talk. So for them, the main challenge is always basically changing from the scale of an experiment that you have in the lab to something that can basically grow in a wafer, right? And wafer means silicon, silicon means linear. So if you want something in which the scales are small, and then there is something that you can put in eventually embark in a device, then well, you end up with linear silicon-based elements, and obviously, as we saw in the talk, that is not enough. So when you get into non-linearities, that's usually energetically very expensive, because I remember from these TDD experiments that I saw, well, what was consuming the most energy was creating non-linearities. In that case, it was with a Mach-Zehnder interferometer, but the rest, it was extremely fast and very cheap from the point of view of energy consumption. So the people I have worked with, the main challenge for them, to achieve things that are small and at the same time they do not spend much energy is non-linearities. That's what they worry the most. When it comes to external memory, is a different story. This reservoir community, computing community that I have been working with, that's something that they think of external. There was, I remember in Nature, there was this discussion or this review of a paper by Google Labs, by Herbert Jega, where they talked about the possibility of putting together well, neurocomputing type of hardware, dedicated hardware with external memory. And but that you would have to Google up, because I don't remember what the discussion there was. But that does exist. I mean, you have these hybrid systems in which, as it was pointed out by this gentleman who asked me a question, usually with reservoir computing, this long-term memory is a problem. So you'd better do it differently. And then when it comes to short-term memory, well, you use the nice features, some of which we discuss here. So this is all I can say. I know is an incomplete answer, and I'm sure that if there are people in the audience who are into hardware, they probably could say something else if they find it appropriate.
Yeah, my question is actually based on the equation that you have on the slide. So if you look at the equation zt plus 1 is equal to h of xt, that's the second equation, yes. So there. So if that is made dependent on the past reservoir states, that is xt and so on, maybe we could reduce the number of nonlinear nodes in the network. So I'm not talking about linear systems. That's
right.
In a network. So I'm just wondering if it's a possibility for the future.
I've been asked these questions. Well, I remember Lorenzo Livi. He asked me that question already, and I told him already more than 1 year ago, I will look into it. I will try to give you an answer, but I still didn't have the time to sit down and think it through. So no, I know the suggestion is excellent, but
because of Tarkan's embedding just needs 2D plus 1. So we may be projecting, we may be using too many neurons in the network. That is what is actually needed. And if we could actually implement a linear readout with the past states of the reservoir as well, maybe, I'm not sure. I was just wondering if there has been any work or any insights that you may have.
Not that I know of, but but that's an idea that several people have in their head, and obviously what you are saying means something only in the nonlinear setup, because in the linear setup, of course, you could recombine everything so that well is what you do in Markov chains, right? So you could just change the dimension so that you go back again to the t and t minus 1, right? But in the nonlinear situation, is a very good question, and I don't know what that gives. So so that's something that I would like to sit down and investigate. But but I did not have the time to do it so far. But it's a very good observation.
No issues. I was just wondering if you had already seen it. Okay. Thank
No,
you.
but I will. Thanks a lot for the question.
Thank you. Yes, yes, that's all. Yeah.
All right. Any last questions or comments or? Yeah, all right then. Thanks again, Juan-Pablo, for the very nice talk, and then to the audience for staying, for coming. And yeah, so we'll probably close the meeting right now, and then have happy holidays and in advance happy New Year, and see you in probably in January, around towards the end of January. Okay, thank you. Bye bye.
Thank you, guys. Thanks, Boumediene.
Bye-bye. Thank you.
Bye.
Bye.